Hello, my name is Pedro Mendoza. I'm a solutions architect in Amazon Web Service IoT team, and today I would like to demonstrate how to set up, configure, and use the integration between the ThingStack and AWS IoT Core. Before we get into the deployment process, I would like to share a bit of context on the configuration we are using today. We have used a ThingStack account on the Sandbox environment in Europe. And on that account, I have configured both a gateway. In this case, I'm using a Bro1 Mini-Hub Pro gateway. And I have also configured an application that has associated a device. In this case, it's also coming from Bro1. It's a temperature and humidity sensor. So the deployment process is fully explained in the ThingStack documentation website. I just want to highlight the fact that in terms of prerequisites, you will also need to create an API key that will basically grant permissions to the deployment mechanism to create certain artifacts. You can see I have already created that API key, so I should be ready to move forward with the deployment of the CloudFormation stack that will actually provision the different resources on the AWS side. Okay, so let's go to the documentation, specifically on the deployment guide. You will find a link to the mechanism to deploy this stack. You just need to select the region. In this case, I will be using US West 2. And then you need to select also the flavor of the ThingStack that you are going to be using. So I'm going for Cloud Hosted, US West 2. When you click there, you will directly transfer to the CloudFormation console. For those of you not familiar with CloudFormation, is the managed service coming from AWS for doing infrastructure as code. So basically, you can, using a declarative approach, define what are the artifacts that you require, and CloudFormation will take care of creating and updating this. So you need to enter a set of input parameters. I will call it TTI-conf, for example. And then you need to select what is the name you want to assign to the thing type that will basically identify those devices that are going to be managed by the integration. You should also select whether or not you want to capture metrics about the devices using the thin shadow mechanism. And you also need to provide what is the cluster address that you're going to be using for your integration. In my case, as I mentioned, I'm using the Sandbox environment in Europe. Make sure that you don't include the protocols and so on. And another very interesting input parameters is whether or not you want to use or enable end-to-end encryption. So if you are dealing with a very sensitive use case and you want to make sure that the LNS doesn't really have visibility on the data being transferred and the data is only decrypted on your AWS account, based on the application session key, then you can enable this option to make sure that the data will reach encrypted till the Amazon Web Service account, and then it will be decrypted there. Right now, I'm not going to be using end-to-end encryption. The final two input parameters are the application ID. So I can copy and paste my application ID. And finally, the application API key that, as mentioned before, should have been created with the right permissions using the ThingStack console. You need to grant permissions for CloudFormation to create certain IAM resources, and you should be good to go. I have already created a CloudFormation stack just to save some time, and you can see here the different resources that have been created. There are a bunch of artifacts, such as Lambda functions for doing all the management of the data being ingested. There are also some, in addition to the uplink and downlink scenarios, there are some interesting use cases implemented in the connector as well for dealing with device creation and device claiming. So you can create devices on the AWS device registry, and these devices will be replicated into the LNS, into the ThingStack. So as I mentioned, I have already created the stack, and now we should be able to actually see the data flowing into AWS IoT Core. In order to confirm that, and you're welcome to refer to the architectural diagram for understanding the details on what are the topics names being used and the different artifacts being deployed as part of integration. But what I will be doing is I will be adding a subscription to the MQTT broker on the AWS IoT core, and I will be basically inspecting the traffic coming from all the topics that begins with the LoRaWAN, which are basically the topics being used by the integration in order to ingest an uplink message into AWS IoT core. In addition to that, I would like to also show you how the metrics about the device are being captured in the shadow document. So this is basically the thing based on the device EUI that represent my LoRaWAN sensor, right? So as you can see here, if I select the shadow, I should be able to see some attributes, like for example, the number of gateways that has been seen in the last transmission, and other parameters such as the signal to noise ratio and so on. So let me try to modify the temperature of the device, and then hopefully once the device reach the LNS, using the integration that we have just deployed, this data should be forwarded into AWS IoT core, and we should be able to see some traffic here on the AWS IoT core broker. Make sure that when you are doing these steps, you select the same region where you have previously deployed the integration, right? So as I mentioned, I'm using US West 2 for the CloudFormation deployment, and I should be able to see the data flowing into the message broker. Might take a while till the sensor. Okay, so now we have it. And as you can see here, in addition to a bunch of metadata information, you can see that the uplink message is, as typically happens in the LoRaWAN devices, is encoded, right? So it's in order to save bandwidth, this payload has been encoded, right? So the first step we need to do here is proceed and decode that uplink message in order to really translate it into useful information that can be used by the application, by our, let's say, downstream consumers. Something I want to mention here is that obviously, especially when you are not using the end-to-end encryption option, you can achieve this decoding step by leveraging the payload formatters that are available as part of the thing stack. However, in this specific demonstration, in order to illustrate how you can use AWS Lambda service to implement this business logic, I will do that by using a Lambda function. So Lambda functions are basically a piece of code that you can deploy in a serverless way, and then the AWS service will take care of dealing with all the infrastructure required to actually run this piece of software, right? So in this case, I'm using a Node as my programming language and execution environment. And as you can see, the function is quite simple. It basically takes a base64 encoded payload, decode it, and then translate it from this binary format into the different attributes of the payload. Specifically, I'm just focusing on a couple of attributes, the temperature and also the battery level. Okay, so this is my Lambda function. So the first thing I need to do is basically create a new rule using the rules engine in AWS IoT core, and that rule will invoke the Lambda function to decode that payload, and I will start by simply republishing the recorded payload into another topic. So I will create a new rule. Let me call that rule TTI conf temperature, and here you can define what is the statement that you want to use for transforming, filtering the data that you are going to be processing. So let me do a bit of formatting here so it's a bit easier to read. So what we are doing here is basically, first of all, you can see that we are only interested in the message coming from LoRaWAN/something/uplink topics, right? That basically means that this rule will only be evaluated whenever there is a message coming from one of the devices associated with my thing stack LNS. And I'm also putting an additional filtering condition, so I'm only interested in those messages whose f_port attribute matches 103. And then what I'm doing here is basically I'm enriching the message by adding a timestamp component, and I'm also invoking that lambda function that we have previously seen, passing as input parameters a couple of attributes, right? The device ID and the encoded payload. As a consequence of the execution of this lambda function, I will get a new message that will contain a timestamp and will contain the decoded payload. So let me save it. And I will add an action. As I mentioned, I will start with a very simple action. You can see you can invoke a really large set of different integration actions, like storing data in DynamoDB or S3, invoking higher order service such as IoT analytics or IoT events, and also you can directly execute a lambda function as the destination for this, right? As mentioned, I will start with something very simple, which is simply republishing the message, and I will select as my destination topic, let's call it TTI/decode. Okay, you need to decide the QoS that you are going to be using. I will use a QoS 0, and you need to define a new role in order to grant permissions to IoT Core in order to perform this action, right? So I will call it like this. Okay, and then we should be good. There's one additional step that is required here. Okay, let's create a rule. There's one additional step, and this is something specific to the fact that I'm inlining the execution of this lambda function, and it's basically granting permissions to the AWS IoT Core service for invoking this lambda function. Right? So that's what I'm doing right now. Basically, using the AWS CLI, I will be adding this permission, right? And specifically, I will be granting the permission to that rule. Make sure that you also select the right region. Okay, I'm having some issue there. It's about the statement ID. So this should fix it. Okay, so we should be good now. And then if I go back to the console and I add another subscription, this is the topic that I want to monitor. And the next time I get a message, if everything was properly configured, I should be able to see both the encoded version of the message before the lambda function is invoked, as well as the decoded version after the lambda invocation is done. Okay, so let's quickly confirm by forcing the device to send an uplink message. Okay, and then we will move into doing something a bit more, let's say, elaborated. Okay, now you can see that we receive a new uplink message here. You can confirm based on the timestamp, and the lambda function was properly executed, and we can see that there has been right now. Actually, I got two messages. There has been the payload has been decoded, and you can see the actual values for both the temperature as well as the battery. Okay, so again, recapping till this point, so we have been able to ingest data into AWS IoT Core coming from the thing stack, and we have also invoked, using the rules engine, an action that is republishing the output of the lambda invocation into a different topic. So what you can actually do once you have your data decoded, you can leverage the AWS platform for doing solutions based on storing data, doing analytics on top of that, doing visualization. And as I mentioned before, you can think as well of more complex scenarios like machine learning and so on. So what I will do is basically I will leverage the integration between the IoT core rules engine and IoT analytics, which is the managed service from AWS, in order to cleanse, enrich, store, and query data that is optimized for IoT data. You can certainly add a complete different rule that will ingest data from this topic and use it for the analytics purpose. But you can also, as I will do now, you can simply add a second action to the same rule. And in this case, as mentioned, I will be sending the data into IoT analytics, right? So you select the destination, and I will use this quick creation mechanism. So let's call this TTI_conf, right? And it will basically create a set of artifacts that basically compose the IoT analytics service. You need a channel just to input the data into IoT analytics. Then you need a data store in order to actually persist the data. You need a pipeline for doing all the enrichment, cleansing in case you require it. And then finally, you can query the data and persist these queries using the concept of a data set, right? And as usual, you also need a role to orchestrate everything in terms of permissions. So we should be good to go. As you can see, it's a really, quick and simple mechanism to create and connect the IoT core rules engine with IoT analytics. And now, again, we should be good to go. And let's take a look into what we have on the analytics space, right? So now we have our data set. I'll try to ingest some additional data here. Just to grab some few data points on our data set. As mentioned, the IoT analytics service has several features that can be quite interesting. As I mentioned, for example, using the pipeline, you can define a set of activities. Like, for example, you can remove attributes from the message. You can add new attributes, like based on calculation. You can also enrich this message using data coming from the shadow document of the device or coming from the registry itself. You can perform filtering. And finally, you can invoke Lambda functions that basically opens a really flexible window in terms of what you can do with the data, right? As mentioned right now, just to keep it simple, I'm not performing any data enrichment using the pipeline, but instead, I will simply demonstrate how you can use the data set artifact. What I will be doing here is I'm actually not interested in consuming the data as it comes from the message. As you can see, it's a kind of hierarchical format, and as you can imagine, data set should be flattened, right? So that's exactly what I will be doing. I will be capturing those attributes that I'm interested in. Going back to the dataset definition. So here, using the SQL query, I can define what are exactly those attributes that I'm interested in. So I will select the timestamp, the device ID, and then the temperature and the battery, right? That should be all what I need. Let me quickly test. Okay. I think the final name I used was not like this. And then we should see like a flattened format of the query. Okay, exactly what I'm looking for, and I should be able to now save this dataset. Obviously, you can schedule like a recurring execution of this data set, so you don't need to manually process. You can select down to 1 minute time granularity, right? So analytics is not especially aimed for near real-time processing, but more on historical type of data processing. So I'm just, again, to keep it simple and not including any scheduling here, let me try to have a second data point, and then we can move forward and perform some visualization of this data. So let me run again the data set. Okay, I have a couple of data points. We can run it one more time in order to basically have additional data. Okay, so now we have our data set available. So what we can do with that? Definitely we can run some analytical models using Jupyter notebooks to implement this. But what I will do today is demonstrate how you can connect this data set with QuickSight for quick dashboarding of this information. So I will add a new data set. I want to highlight that all the services that I'm demonstrating today are managed service. That basically means that you as a user don't need to deal with the operational pain of dealing with the capacity of the services, what happens if you have an increase on the load, what happens if you have a failure on one specific, let's say, instance of the hardware, and so on. This is something that AWS basically takes the operational pain. So I will create a new data set. Again, QuickSight supports integrating with a bunch of different sources, both AWS data sources, but also third-party, including IoT analytics. I will just select my data set, and it will import the data. I will add a new field in order to properly model the daytime as such. I will use this built-in function, which is epoch time. And what I'm doing here is basically I'm producing a daytime field from the epoch field. So we should be good. You can see now we have a couple of data points. Unfortunately, we have the same value, so it will not really be too fancy in terms of visualization. But I hope it really illustrates the value of QuickSight, right? And then finally, I will create a visualization. I will select the type of chart that I'm interested in, and then I will basically drag and drop the different attributes here. So I will use this daytime. I will aggregate at the minute level, and here I will basically plot the temperature. I select the average value for it. You can also add additional fields, like for example the battery. Okay, same thing. You can select which aggregation you want to use. As I mentioned, given that we only have 2 data points, it doesn't really brings much value. But as you can imagine, as you capture additional data, and you can also automate the refresh of the QuickSight data set, then you can turn the data coming from the LoRa devices into actual business value. So again, this is a very simple demonstration on what you can do with this integration between the ThingStack and the AWS IoT Core by basically leveraging the power or the convenience of using this LoRa data in order to build solutions on AWS. This is just a very brief introduction to the topic, and it only covers the uplink use case. As mentioned, the integration also has support for downlink, as well as other use cases like claiming devices, creating devices, and so on. You're more than welcome to review the documentation and give it a try. We have also write a blog post on the AWS partner blog detailing how to achieve that. So that's all I want to show today. Thanks a lot for your attention.